On this page of notes, we're going to take just one last look at understanding the work done by gravity, path independence, but also the work we would be doing if we were manipulating the object through the different paths that are shown here as well. And the one thing we definitely need to know is that the path that is shown here is a vertical path. So you have to think of it standing up in the y direction so that you're working directly against gravity when you're moving upwards the 10 meters or up or down in the 5 meter distance as well. So what we have here is that we're going to neglect air resistance, so we're not including any air resistance. We're starting at position A, and we want to know the minimum work needed. Now, again, work and energy problems, you have to be very careful with the wording in the question. Is it the work done by you, an external force? Is it the work done by gravity? Or is it the net work being done that they're looking for in the question? So here we're looking at the minimum work needed. Now this is needed by you to move the object from position A to position B. Now to find the minimum work needed by you, notice we're going to start our analysis by looking at the work done by gravity. So in terms of going from position A to position B, we know gravity does no work for any of the side-to-side part of the motion. It's only the vertical part of the motion that will enter into our calculation. The force due to gravity is, of course, down. The delta y in this case from A to B is up, so that's where the cosine of 180 comes from, giving us the negative here. And we have a 1 kilogram mass times 9.8 times the 10 meters in the y direction. So the work done by gravity is going to be negative 98 joules. So that means the minimum work needed from you, a force applied, is going to be positive 98 joules. So you can see where even if you're looking for the work done by an external force, sometimes we have to focus on the other forces in the problem and then just realize that the work needed minimum would be able to match the energy taken out by the other force. How about the minimum work needed to take the object, this 1 kilogram mass, from position C to position D? So now we're going down 5 meters. So the force due to gravity is downward. Now from C to D, that's downward. So now gravity is putting in energy plus 1 times 9.8 times 5, or plus 49 joules of energy that gravity wants to put in. So if it's going to move at constant speed, we can't let there be any net transfer of energy to change the speed. So that means the work we need to do would be negative 49 joules. Okay, D to E, we've talked about. Sideways motion does not matter, right? So there is no change in the y direction, right? D and E are at the same y position. So as long as there is no change in the y position of the object, then the work needed is 0 in the absence of friction. Remember, we said the force needed would be 0.00000000001, a smidge, but we say 0 is the number we use for our answers, and so the work needed is 0 joules. How about round trip? Well, round trip, again, whether it's moving sideways or whether we start at the same y position and end at the same y position, we have delta y equals 0. So the work done by gravity equals 0, and that means the net work needed by force external would also be 0, because all of those positives and negatives that we calculated, they would all balance out perfectly as long as delta y is 0. So we'll talk again more about this in class. I think we have just a couple of homework problems on this topic since we've pretty well covered it by this point. And we're going to move on to calculating the energy transfer by forces that now vary. So they won't be constant forces like mg, and that'll be fun to look at as well.